In this lesson, we're going to apply what we've recently just learned about acids and bases, and we're going to apply it to the concept of equilibrium. In the first part of this lesson, I'm going to talk about the autoionization of water, but in order to understand what the autoionization of water is, I've got to go over two specific terms, amphoteric and amphiprotic. Now, water is amphoteric and it's amphiprotic, so what exactly does that mean? Well, amphoteric means that a substance can act either as a base or an acid, and amphiprotic means that a substance can accept or donate a proton, which makes you think that these are the same terms, but for the moment, yes, they are, because the only definition of acids and bases we've come up with so far are Bronsted-Lowry acids and bases, other than your Arrhenius acids and bases. However, we have one more definition of acids and bases, which is Lewis acids and bases. And in that definition, we're not dealing with protons. So, moral of the story, water can act as either a base or an acid, and it does so by either accepting or donating a proton. Well, what does that look like? Well, water, as we saw in previous reactions, can either act as an acid or a base, or if it's reacting with itself, one water molecule can act as a base and the other one can act as an acid. And this reaction is called autoionization because you're producing ions, but water is doing it to itself. So if you look, the water on the far left-hand side, that donates a proton to the water next to it, which serves as a base because it accepts the proton. And so what you produce as a result is a hydroxide ion and a hydronium ion. Now, water mostly exists as the molecule H2O and not as these ions. And that's why water does not conduct electricity, because the majority of water exists as a molecule and not as ions. If it didn't, if in fact the right-hand side of this equilibrium were favored, then pure water would be able to conduct electricity, but it doesn't. So the water that you drink for the most part is just H2O, although there are a couple of ions in there. It's not significant enough to change the physical properties of water. All right, so we're going to take this concept of the autoionization of water, specifically this reaction, this equilibrium reaction, and we're going to come up with a new equilibrium constant, and specifically that equilibrium constant is called the ion product constant. And the ion product constant is Kw instead of Kc or Kp. It's Kw, and that equals, notice, just as a review from equilibrium, you do products over reactants. Well, your products are hydroxide and hydronium, so you've got those concentrations. The reason why we exclude water, liquid water, is because it's a pure substance. And so hydronium ion, the concentration of the hydronium ion times the concentration of the hydroxide ion, those multiplied by each other, that gives you 1.0 times 10 to the negative 14th. Because remember, as long as we're at constant temperature, your equilibrium constant doesn't change. Now, this value is extremely important as we prepare to be calculating pH and pOH, as you'll see in just one second. So just as a review, if your concentration of hydrogen ions is higher than the concentration of hydroxide ions, that means you have an acidic solution. Keep in mind, hydronium and hydrogen ions, we're going to be using them interchangeably. If the concentration of hydrogen ions and hydroxide ions is the same, then you have a neutral solution. And finally, if the concentration of hydroxide is higher than the concentration of hydrogen ions, then you're going to have a basic solution. Notice for all of these that your ion product constant, your Kw, is still 1.0 times 10 to the negative 14th, no matter what's happening to your concentration of hydrogen ions or hydroxide ions. So looking at this example here, it's asking us to calculate the concentration of hydroxide ions. We know the concentration of hydrogen ions. Therefore, we can use this formula, your ion product formula, and then just plug in the values. I know that my Kw is 1.0 times 10 to the negative 14th. I know that the concentration of H plus is 5.6 times 10 to the negative 6 molar, and so I'm just calculating for my concentration of hydroxide ions, and I find that it's 1.8 times 10 to the negative 9th molar. So the second part of this question asks you to indicate if the solution is acidic, basic, or neutral. Well, since 1.8 times 10 to the negative 9th is a lower concentration than 5.6 times 10 to the negative 6, that means that my solution is going to be acidic because I have a higher concentration of hydrogen ions than hydroxide ions. Let's now actually look at pH. You might have looked at this concept in a previous chemistry class or even in middle school, but we're going to look at it in quite a bit more detail now and learn how to calculate it based on concentrations of hydroxide ions and hydrogen ions. Keep in mind, thinking back or looking back at your notes, concentration of hydrogen ions is extremely low, and so what we've created to make these values more manageable is this pH scale. And so the pH simply equals the negative log of the concentration of hydrogen ions. So if you notice here, while a solution is acidic if its concentration of hydrogen ions is larger than 1.0 times 10 to the negative 7th, meaning it's going to be a higher concentration of hydrogen ions than hydroxide ions, your pH has to be less than 7 for it to be considered acidic. Similarly, if it's neutral, if your solution is neutral, then the pH is going to be equal to 7.00, and if it's basic, while the concentration of hydrogen ions is less than 1.0 times 10 to the negative 7th for it to be basic, the pH is going to be larger than 7.00. Just like pH equals the negative log of the concentration of hydrogen ions, the pOH equals the negative log of the concentration of hydroxide ions. And if you do a little bit of manipulation, what you can realize is that pH plus pOH, that actually equals 14.00. And I got that by finding the log of your Kw, of your ion product constant. So pH plus pOH equals 14.00. That makes it really easy to convert between pH and pOH, as you'll see in just one sec. So let's look at this example right here. I give you the concentration of hydrogen ions. I asked you to calculate the pH, the concentration of hydroxide, and the pOH, and finally to decide whether the solution is acidic or basic. Now, since I give you the concentration of hydrogen ions, I can easily find the pH. All you've got to do is take the negative log of that value. And what you should find is that your pH equals 5. Since my pH is 5, which is less than 7, I know that my solution is acidic. Keep in mind when deciding whether a solution is acidic or basic, you want to look at your pH. Now, since I know my pH is 5 and I know that pH plus pOH is 14, then I know my pOH is going to be 9. And finally, I can calculate my concentration of OH if I keep in mind the fact that the pOH equals the negative log of the concentration of OH minus. Well, to solve this, I'm going to move the negative sign over to the 9, so it's going to be negative 9 equals the log of concentration of OH. Keep in mind, since I didn't write anything for log, it's implied that the base for log is a 10, so the number below is a 10. So the concentration of OH is simply going to be 10 raised to the negative 9th. That equals your concentration of OH. If you need review for logs, I would go to the appendix in your textbook. Now, the pH depends on the strength of the acids and the concentrations because weak acids and bases do not dissociate completely because they are weak electrolytes. So as a result, we can't simply assume, for example, in this problem, that 2.50 molar OH is produced. Instead, we actually have to calculate how much hydroxide ions, what concentration of hydroxide ions are being produced. Well, if I have 2.50 molar ammonia and it only ionizes 5%, what that means is that the concentration of hydroxide ions is only going to be 0.13 molar. Now I can take this value and I can actually calculate my pOH by plugging it into the negative log of the concentration of hydroxide ions, and I get that my pOH is 0.89. Now since pOH plus pH equals 14, I can then calculate and find that my pH is 13.11. So keep in mind, to get a strong and a weak acid to have the same pH, or to get a strong base and a weak base to have the same pH, a higher concentration of that weak acid or that weak base is needed. Simply because with a weak acid and a weak base, you don't have 100% ionization. In this problem, I'm given the concentration of my acid and I'm asked to find the pH. Well, looking at this problem, even if I don't look at the title of a section, I know that perchloric acid is one of my strong acids, which means that it's a strong electrolyte, which also means that 100% of it's going to dissociate. So I'm going to have 0.040 molar concentration of hydrogen ions. So I could just plug this in right here to my pH formula. So my pH equals the negative log of the concentration. Well, I know the concentration of hydrogen ions is 0.040 molar. And that's going to equal 1.4. Now, I can do it that way, but I want to introduce the concept of using ice charts in determining pH. So I'm actually going to do it using ice charts. Well, I know that the dissociation of this acid, HClO4, I'm going to do it without writing water. You can write it with water, and it would just make a hydronium ion. But that's going to produce hydrogen ions and perchlorate ions. Okay. Now I'm going to use ice chart just like what I did in my equilibrium unit. ICE, I initial change and the equilibrium concentration. I know that I start with 0.04 molar of my perchloric acid, 0 molar of my two products. And since this is a strong acid, I know that I'm going to lose all of my acid. It's going to completely dissociate. So in the end, at equilibrium, I'm going to have 0 molar of my acid. Since this is minus X, this would be plus X. My X is going to be 0.04, which means my concentration of hydrogen ions is going to be 0.04. And perchlorate, same thing. And so what I then can do is say, all right, my concentration of hydrogen ions is going to be 0.04 molar, and then I can plug it in to my formula for pH. Now, if I didn't have a strong acid, this value would not be 0.04. It would be X, and I would have to solve for that because in weak acids, you don't have 100% dissociation of that acid.